Okay, so let's get started with some new stuff after our review of U substitution. So what we're going to start off with first in this class is some applications of integration. So this is going to be using what you learned in using definite integrals in Calc 1 to some applications. We're not going to get to all the applications that we're going to get to in the class right now because many of the applications require you to integrate more complicated functions. So that means that we're going to have to come back to those after we've done integration techniques. But we'll be able to go through a few here. So one of the most basic applications of integration is related to something that you should have done in Calc 1. So when you first studied integration, you learned that the definite integral has this nice geometric interpretation as the area under the graph of a function. Now that's provided the function is non-negative. If the function is negative, then it's possible to think about net area, where the area below the x-axis is counted as a negative area. But just for the sake of argument, if it's non-negative, then the integral simply represents the area of a region. But we can use integration to find other areas, so other regions that don't exactly fit this situation. And one good example of this is the area between two curves, where each of the curves are graphs of functions. And for all of these applications, so not just area between curves, but for different physics applications that we'll do later, what we have to do is set up a Riemann sum, and then we're going to take a limit. And anytime you take a Riemann sum and you take the limit of it, you get a definite integral. That's what the definition of the definite integral was. It was defined as a limit of Riemann sums. What's different now from Calc 1 is in Calc 1, really the only application of definite integrals that you knew was the area under the graph of a function. So a lot of Calc 1 students have in their mind, when they finish the class, they think the integration, the definite integral, and area under a curve are kind of synonymous, like they're equivalent. And that's not really the case. Integration, the definite integral, can be used to evaluate many different types of problems where you're adding up a bunch of little things. And the area under the graph of a function is just one of those examples. It's the most useful example to think about what an integral is. There's lots of other examples we'll go through, and this is the first. So let's start with an example, and then we'll talk about the general case. So we're going to find the area of the region bounded by the graphs of two functions. So y equals x squared plus 1, y equals x equals negative 1, and x equals 2. So what I'm going to do is go ahead and graph these in Desmos, because Desmos can graph a whole lot better than I can graph by hand. So let's go ahead and look at those. Okay, so here we have the graph of x squared plus 1. Of course, that's just an ordinary parabola shifted up 1 unit, so it's this graph right here. And then y equals x is just a line with slope 1 through the origin. And it's also bounded by these two vertical lines, negative 1 and 2. Now notice, if we were just looking at if we're just looking at x squared plus 1, we'd just get the area that's underneath the graph there. So we would just get this area. Right, so this is the area that we would get if we were integrating x squared plus 1 between negative 1 and 2. But what we're doing now is we're finding the area, we want to find the area between the two graphs. So we want to find this area. So let's think about how we can set this up. What we're going to do is chop this region up into a bunch of little pieces, and then evaluate a sum. So let's take two very small points here. Let's say between 1 and 1.1. Okay, so we're looking at this little purple region here. So this little strip. This is from 1 to 1.1. So how can we estimate the area of this little strip? Well, we could approximate it with a little rectangle, just like you did for area under the curve of a graph of one function. So what's the width going to be? Well, the width is going to be delta x. And the height, now this is the important part, the height is always going to be the difference between the y-coordinates. Well, the difference between the y-coordinates is going to be, in this case, x squared plus 1 subtract x, right? So that's our two functions are x squared plus 1 and x. So if we take x squared plus 1, subtract x, that's the difference in the y-coordinates. So that's the height of the little rectangle. And we can do that for a bunch of little rectangles from the left all the way sweeping out to the right. So let me go ahead and I will sketch this here. Okay, and what we're going to do is think of a small little rectangle here. Let's say it looks like this. So that's going to be the parabolic part up top. There's a straight line segment on the bottom there. And we're thinking about it's going to be very thin, so something like this. Okay, so we want to know what's this area. So we approximate this. With a rectangle. This is the actual region is not really a rectangle. We're going to approximate it with a rectangle. So it's going to have width delta x, and then the height here, since this is x squared plus 1, that's the y-coordinate, and the y-coordinate down here is y equals x. Then the difference between the two, this here, is x squared plus 1 subtract x, or x squared minus x plus 1. So then, what do we do after this? Well, we want to add up all the areas of the rectangles. All the areas of the little rectangles. And I'm going to kind of skip a little bit of the steps here. What I'm going to do is just write what would be the form of the Riemann sum, because you should be familiar with the Riemann sums you did from integration before. So it would be a sum, say, from I equals 1 to n of x squared plus 1 minus x delta x. So these would be xi, where the xi's are sample points. Right, so to actually evaluate this height here, we have to take a sample point here. So we just take some xi inside here. So it's really xi squared minus xi plus 1. So it's a sample point in the subinterval. Okay, but this is exactly a Riemann sum. So if we take the limit as delta x goes to 0, and as n goes to infinity, then we get a definite integral. Okay, and I will give you a minute. You want to pause the video and just write down what that integral is going to be. And you can go ahead and evaluate it too. It's a polynomial, so you should be able to evaluate it. Okay, so you should have gotten the integral from -1 up to 2 of x squared minus x plus 1 dx. Now notice, you had an interpretation of this integral before, but it would have been the area under the graph of this entire x squared minus x plus 1, that single function above the x-axis. Now we have this integral, but it's not coming from a single function. It's coming from the graphs of these two functions. It's the difference of these two. It's the difference of x squared plus 1 and x. So we integrate this, so x cubed over 3 minus x squared over 2 plus x from -1 to 2. And I'll leave the details of this to you, but you should end up with 9/2, 4.5. Okay, so let's think about what we just did here, and let's think about how this would look in general. So in general, let's suppose that we have two functions. Okay, so we have these two functions here. Now, notice this is going to be between 2 points here. This is going to be between A and B. So our assumption is that f of x is bigger than or equal to g of x between A and B. Now, we'll go over in the next little subtopic video, we'll go over what's the case if the graphs happen to cross, or what if it's not the case that one's always bigger than the other. But let's just say that one of them is always bigger than or equal to the other one on some interval from A to B. Then we would get the Riemann sum just in the way that we just did. It would be this. It would be the sum from I equals 1 to n of f of xi minus g of xi, where xi are, again, some sample points, times delta x. And just as in the previous one here, we can assume that these are all equal sub-intervals, so these are all b minus a over n. So this is our Riemann sum, and then we take the limit. Take the limit as delta x goes to 0, and as n goes to infinity, and we get the integral from a to b of f of x minus g of x dx. So that is the integral that gives us the area of this particular region. Okay, so let's look at one more example to wrap up here, and this one has a little bit of a twist to it. It's still just between two curves, but it's slightly different. So let's look at that one. So this one says, find the area of the region bounded by these graphs, y equals negative x squared and y equals x to the fourth minus x cubed minus x squared plus x minus 1. Now, one thing to notice here. I only gave you the graphs of the functions. You might be saying, well, wait a second. What are my limits of integration going to be? They didn't give us the vertical line segments that are going to tell us, where the region starts and stops. Well, in that case, what that means is the two graphs are going to intersect, and we have to figure out what those intersection points are going to be. So let me show you the graphs of these. Okay, so here's the graphs of minus x squared, which is obviously the parabola that's opening downward, vertex at the origin, and then this fourth degree polynomial graph, x to the fourth minus x squared, x to the fourth minus x cubed minus x squared plus x minus 1. Now, in general, when you have two of these, unless they're really nice functions, it's very difficult to figure out exactly where they'd intersect. In this case, we can, and I'll show you how. Although from the graph here, you can inspect from the graph that it looks like negative 1 and 1 are where they intersect, and we'll verify that. So what we're looking for is this region here. Okay, so that's the region we're trying to find the area of. So same situation, we've got a graph of a function on top, we've got a graph of a function on the bottom. So we're going to take the difference, but the only difference here is we need to figure out where the limits of integration are. And I'll show you how you can do that right now. So to find the points of intersection here, we have to solve these equal to each other. So we need to find minus x squared. Where is that equal to x to the fourth minus x cubed minus x squared plus x minus 1. Now normally a fourth degree equation like this would be pretty difficult to solve, but we luck out here because minus x squared, and so we just end up with x to the fourth minus x cubed plus x minus 1 equals 0. And this, fortunately, we can do factoring by grouping. If we factor out x cubed here, now then we get x cubed plus 1, x minus 1, and then this is saying x cubed has to be negative 1, so that's x equals negative 1, 1. Okay, so we do end up with those 2 points. So how would we set up this integral? Well, it would be the integral between negative 1 and 1 of, now here's what you have to be careful of. You have to get it's the top function minus the bottom function. So it has to be the function that's bigger, not the one that's necessarily a higher degree polynomial or the one that symbolically looks bigger, the one that's actually bigger. Sometimes the bigger function doesn't look bigger if you just look at it symbolically. So the bigger one here was actually the minus x squared, right? That was the top function. So it's going to be minus x squared minus x to the fourth minus x cubed minus x squared plus x minus 1. Okay, so here's upper function, lower function. Upper minus lower. Now, again, we've got some terms that cancel out here. There's the minus x squared. There's a minus x squared. If you distribute the minus here, that's a positive x squared. So really we just end up with minus x to the fourth plus x cubed minus x plus 1. Now, there's even another thing we can do here. So I'll let you stop and think if you remember something from Calc 1 that will simplify this integral even more. Okay, so you should have remembered that when you're integrating from minus a to a, like here negative 1 to 1, since that interval is symmetric about the origin, any function that's odd is going to evaluate to 0. So we have an x cubed term here, so we can just ignore that. That's an odd function. Minus x is an odd function. So really it's just the minus x squared, the minus x to the fourth plus 1. So this becomes minus x to the fifth over 5. And actually you could use the property again, right? You could make this, in fact, let's do that. Since this is, so these are even, and then these two terms are odd. So the odd powered terms went away. The even ones, now we can actually integrate from just 0 to 1 as long as we double it. So when you're integrating an even function from minus a to a, it's twice from 0 to a. So minus x to the fifth over 5 plus x from 0 to 1, provided we take 2 times it. So that's going to be 2 times. And the nice thing about this is now, at 0, we know that all those terms evaluate to 0. So that saves us computation. So we end up with 2 times minus 1/5 plus 1. So what does that make? 4/5 times 2, 8/5. So that goes to show you another example there. We get area exactly equal to 8/5. So in the next section, we're going to do some examples where the function graphs may cross. So if they cross, we'll go over what to do there. And also, what if we're looking at x as a function of y instead of y as a function of x? So we can also do that, and that introduces also some problems where you might have to choose which variable you want to choose to integrate with respect to. So we'll look at those examples in the next video.